This is the second video from section 4.4, Properties of Bases. And in this video, I want to, sorry, let me zoom out a little bit here. In this video, I want to talk a little bit more about bases, look at some facts about them, some theorems about them, and see if by picking those apart and really trying to understand what they're saying, we can get maybe a clearer or more useful kind of perspective on bases in general. By the way, bases are just the plural of basis, so I'll use those words both. So let's start here with Theorem 4.8 from your textbook. It says, let the set V1 through Vn of vectors, so there's n vectors here, be a basis for vector space V. Right, and to be a basis, remember that means this set of vectors spans V. Any vector in V can be written as a linear combination of these vectors. That's what it means to span V. And this is a linearly independent set of vectors. That was the definition of our basis here. So this theorem is saying if we have that basis for V, for the vector space V, and we also have a set of vectors W1 through Wm, so m vectors here, n of them here, if this is a set of more than n vectors in V, so the number here is more than the number of vectors here, then this must be a linearly dependent set. We can think of this as saying is that the number of vectors in a basis is actually in a certain basis for a certain vector space is actually the maximal number of linearly independent vectors you can have in that vector space. You take a set of more vectors than that, you won't have linear independence anymore. You get dependence. One of these vectors is expendable, at least one, right? Can be written in terms of the others. So, like I was saying, just stated here in words, no linearly independent set of vectors in any vector space V can have more vectors than any basis of V. Otherwise, this theorem applies and you get linear dependence. If you had a set that was containing more than n, you get dependence. Well, an immediate result of that fact, this fact that we just talked about, is that, well, this fact applies so long as we have a linearly independent set of vectors here, right? So long as that's what we put here. But a basis is a linearly independent set of vectors. So if we replace this statement, linearly independent set of vectors, with a basis, the statement's still true. So we can also say that no basis of V can have more vectors than any other basis of V. This is very nice. It gives us almost immediately Theorem 4.9 from your textbook, which just says that all bases of a given vector space contain the same number of vectors. All right, this is almost, I don't want to say trivial, but it's almost trivial to prove from these facts we've established. We can just say, for example, to prove this, consider any two bases of your vector space V, maybe call them V1 through Vn and W1 through Wm. All right. Then by the facts we established up here, no basis of V can have more vectors than any other basis of V. Well, you're saying we have two bases, one with n vectors, one with m vectors. Well, then right away we get that this guy can't have more vectors than this one. N can't be bigger than m. So we get the mathematical statement that n must be less than or equal to m. Right? Can't have more vectors here than are here. But that same argument holds if we look at it in the reverse order. Can't have more vectors here than we have here. Can't have more w's than v's. Since they're both bases, works in both directions. So we get also m is less than or equal to n. Taken together, these inequalities are only solved by m equaling n. So this tells us m equals n. The number of vectors in any basis here is the same as the number of vectors in any other basis here. Right. This proves this theorem 4.9, just using these facts we wrote up here. Right. By the way, in case you're wondering about this little result down at the bottom, well, we're saying n is less than or equal to m, but n is also greater than or equal to m. The only way you can be both less than or equal to and greater than or equal to something else is by being equal to. The less than and greater than are not compatible, but the equal to is the only possibility. Excuse me. So let's look a little bit further here. I want to go through some more facts, maybe some definitions. Starting here, we can say this is a definition we'll use, all right, that's kind of motivated. Well, let's take a look at the definition first. If a vector space V has a basis containing n vectors, then we say that the dimension of V is n, and we write that dim of V equals n. Right? This kind of makes sense. We'd want to define something like this because we already said that no matter what basis we look at, they're going to, of a given vector space, they're going to have the same number of vectors. So something about that number of vectors in any basis of a vector space is some kind of intrinsic quality of the vector space. That number describes the vector space in a meaningful way, so we give it a name. We call it the dimension of the vector space. Let's look a little bit further here before we get to an example. All these definitions we've looked at, if you remember all the way back to the definition of a basis, they actually required a set, all the definitions of basis that we've looked at require a set containing a finite number of vectors. So if you think about that, it might be concerning that not all vector spaces necessarily can be described by such a finite set. For example, the set of all polynomials of any degree. You can't describe that with a finite number of vectors in that in the polynomial space. Maybe we'll get an example like that later. But for example, think of that polynomial example. How do you write any polynomial of any degree in terms of a finite set of polynomials? Don't think you can do it. Anyway, so in the case that a finite set of vectors is available to form a basis, we call the vector space finite dimensional. We can use this definition of dimension in that case. It'll be some finite number. If no such finite set of vectors exists, we call the vector space infinite dimensional, like the vector space of all polynomials. So let's see here. Let's see this last little theorem before we see an example. Theorem 4.11 here. It just says if V is a vector space of dimension n and S is a set of vectors v1 through vn, so that's n vectors in this vector space, then what can we say? And this, I think, is just a couple more facts kind of to add to the toolbox to build our intuition about these bases and build our intuition about these things. So let's see. What can we say? First of all, we have this set S. We're going to say if S is linearly independent, then it turns out that's all you need to say that S is a basis of V. A vector space V. So this is kind of big already. We're saying if we know the dimension here, and we've got a set with that many vectors in it, then it's saying we don't necessarily have to check span. We get a basis for free if we can just show linear independence. Right? A basis requires the set to span the vector space and to be linearly independent. Here we're saying if we know we have the right dimension, the number of vectors in our set, we only have to check that linear independence. And we're going to say part B of this theorem is just going to say kind of the other half of this puzzle works the same way. We can say oops, messed up here. Let me fix this. We should say if S is linearly independent, then S is a basis, right? If we know we have the right number of vectors, all we need is to know they're linearly independent to know we have a basis. On the flip side, we can also say here, if S spans V, same deal. Again, if we know we have the right dimension to fit our vector space, we only have to check that the set spans the vector space to know it's a basis. Without knowing the right dimension and that you've got a set with that many vectors in it, then you have to check both of these requirements, linear independence and that it spans the space. But if you already have a set that's got the right number of vectors to match the dimension of your vector space, you only have to check one or the other. You get that it's a basis for free. Okay, so from here, let's go ahead and take a look at an example. Let's see this. There'll be a couple parts to this example. Okay. Let's call this first part, part 1. Let's determine a basis for a subspace. Of R3. And let's write down its dimension. Let's say that the subspace we're describing here, that we want a basis for and the dimension of, is the subspace W, I'll call it, of vectors of the form A, B, let's see, we'll do this a little different. A, 2B, A plus 3B. Right? Where A and B are real numbers. We won't write it, but since we're in R3, let's say it's implied. So we want to determine a basis for the subspace of R3 and write down its dimension. The subspace is all vectors of this form here, so notice we can say given a vector of this form in this subspace W, we can write this guy as kind of splitting up the A and B stuff. Right, notice what we get from the previous line does kind of expand into this form, if we please. And from each of these vectors, we can factor out the arbitrary scalar A and B. Right, so we can write any vector that's in W certainly can be written in this form, meaning the set here spans the space. W. And right away, notice here, we don't really know the dimension of W, so we do have to check linear independence as well. But notice 1, 0, 1 is not a scalar multiple of the other vector, 0, 2, 3, which is all you have to check for a linear independence of two vectors. So it means the set containing these two vectors is also linearly independent. Let me free up some workspace here. All right. Well, now that we have that this set spans the subspace and this set is linearly independent, we know that makes a basis. That is a basis for W. And notice that if we think of all the vectors that can be obtained in R3 by taking linear combinations of these two vectors, that's just the plane, right? In R3 we can think we've got some vector maybe here, maybe some vector over here. We're really thinking that those two vectors, the subspace they kind of generate is really just this plane here, right? This plane embedded in 3D. So we can say this plane that I've labeled is W, right? That makes up W. It's the plane spanned by these two vectors, which I'm just saying are 1, 0, 1 and 0, 2, 3. I didn't draw them accurately for those coordinates, for those components. But we can think of whatever these two directions are. Think of the plane swept out by those two directions. That's our plane that's really given by the subspace W. So we found it, and we know here that since this basis has two vectors in it, we can say the dimension of W equals 2 by definition. Now what I want to do just to wrap up here is to also ask a side question out at the end, kind of an extra problem. Let's say add another vector to that basis so that the resulting set is a basis for all of our 3. Right, so how can we do this? Right, we're just saying what other vector can we add in here so that the resulting set is a basis for all of our 3? Well, we already know how many vectors we would need in R3. Right, in R3, that is a 3-dimensional space, right? So we would need 3 vectors to describe this guy. Or you can think, why is it 3-dimensional? We can see it's 3-dimensional because we know the standard basis for this R3 space is a set of 3 vectors. So since there's 3 vectors in this basis, we know it's 3-dimensional. So we know how many vectors we need. We just need, on top of these 2, we need 1 more. Well, so long as we have a set of, maybe I'll call it Q's, that missing vector, so long as we have a set of 3 vectors here in R3, as long as this guy is linearly independent with the other 2 all combined, we know we have, according to this theorem above, we know that so long as our set is linearly independent, that will be a basis, so long as we've got the right number of vectors here, 3 of them, Q, 1, 0, 1, 0, 2, 3. So we just need Let me say that out front. Yikes. We just need this set here to be linearly independent then it will also be a basis for R3. By theorem, whatever. Let's write it down by theorem. 4.11a. Right. Well, so this is easy to do. We just need to find this vector q that's linearly independent with these guys, meaning cannot be written as a linear combination of these guys. But remember, these guys exactly describe the space W in the way that anything in W can be written as a linear combination of these guys. So all we have to do is take a q that's not in this plane, not expressible as a linear combination of these guys. Well, that really just means, in other words, we need q not in W, not in that plane, which is fully described by linear combinations of 1, 0, 1 and 0, 2, 3. Well, so yet another way to rephrase it. We need a vector q not of the form that all vectors in W have. A, 2b, a plus 3b. We just need any vector that's not of that form. For example, take q equals, I don't know, 1, 2, 0. That'll do it, right? This is not of the form a, 2b, a plus 3b. A plus 2b in my case would be, that would mean b is 1. That would mean we need a 4 here to be in W. We're not in W. So there we have it. There are many correct answers. This is one. This is a basis for R3. Okay, I think that video is plenty long enough, and the last one we'll wrap up with a couple more facts and then some examples to wrap up.